Good morning, everyone. In this video, we are going to talk about the basic logic gates, which are basic building blocks of our computations and all the computation, modern computation, and the computers. So, the the foundation of computation or data, which we have, is one bit. So, how do we represent a bit physically? If we have current in a wire, then it is considered as 1, and if not, it is considered as 0. So here I have a basic switch and I can give input from here, and here is my output. This is my input 0, let's say. So this is my input and this is my output. So let's see, if I give the input 1, the output is 1, and if I give the input 0, the output is also 0. This configuration is called a buffer gate, where the output is equal to the input. So let's see how we can use this buffer gate to make a little bit complex logic. So see, here I have two switches, like you can say two buffer gate connected in parallel. When I give the input 1 in one of the buffer gate, now I get the output 1, like this. And if both of them are 1, the output is also 1. And when both of them are 0, then the output is 0. This configuration is called OR gate. And it is represented in electronics. This is represented as this. This is my OR gate. When I toggle this to 1, my output is 1. When both are 1, then also the output is 1. When B is 1, then also output is 1. And only when both of them are 0, the output is 0. Let's move on to the next logic gate. Yeah. Here we have connected two buffer gates or two switches in series. So if I want to get the output 1, I would have to turn both of these switches on. So when both of the inputs are 1, then only output is 1. If either of them is off, then the output will be 0. So this configuration is called AND gate. And you can see AND gate is represented with this symbol. So see, when I'm toggling both of them 1, then only the output is 1. Next, we have few more logic gates. Let's talk about them quickly. This one, first we have a NOT gate. It simply flips the input. When we have 1 in the input, then the output is 0. When we have 0 in the input, the output is 1. Next, this is the buffer gate I showed you earlier, configuration. Next, the AND and OR gate. AND gate is like when both of them are 1, then only the output is 1. OR gate is when either of them is 1, then output is 1. Next we have, this is my NAND gate. This is AND gate, but the output is flipped. So when both of them are 0, the AND gate output should have been 0. But here we have a NOT gate, which has flipped the output, and we are getting 1 at the output. So when I toggle this input 1, then nothing happens. But when I toggle both of them 1, then the AND gate output should be 1, but we have a NOT gate here, so the output is flipped. Again, same with this one. This is the NOR. So when both of the input is 0, I'm getting the output 1. But when I toggle any one of them 1, the output is 0, because OR gate output would have been 1 with this input 1 0. But we have a NOT gate here which has flipped the output, and I am getting 0 here. Next, this is a somewhat complex, a bit complex logic gate with this is called exclusive OR gate. Output of this will be 1 when either one of the input is 1. If both of them are 1, then the output is 0. And if both of them are 0, then also the output is 0. So it gives me 1 when either of the input is 1. Like this. And this is the XNOR gate. This is the exclusive OR gate, but the output is flipped here, like before. So when I toggle this 1, 0, I'm giving 1, 0 at the input. I'm getting 0 at the output. 1, 0 in the XOR gate would have been 1. But in the XNOR gate, it is giving me 0. So these are the basic logic gates we have. Next, we will combine them and build more complex circuits like adders and multipliers. And then we'll move on to making ALUs, arithmetic logical units, then control unit, registers, RAM, ROM, and how all these work together to form a whole computer. Okay, I'll see you in the next video.